Hello, everybody. Welcome back. In this lesson, we will go over some mixed derivative computations together with some interesting facts. A few uh, different examples that would apply uh, the idea of the derivative in a certain way. So, to begin with, first of all, what do we mean by mixed derivative computations? We already learned a bunch of derivative formulas together with rules of differentiation. So when we consider these rules of differentiation, for instance, linearity properties, product rule, quotient rule, and the chain rule, we can combine them in certain problems. That is exactly what I'm going to deal with in the first couple of examples. So I'm not planning to make it too busy, except for giving you a few sample problems. So example number one. So here you can see a function. The construction is pretty clear. The overview tells us the separation is the product. And we can understand when it comes to each individual component, there is either one of the properties or a combination of properties needed for the differentiation component. So I will just work with this one right away. First of all, I need to have the product rule. I need to use the product rule because of this product. So first I'm going to grab the first function. I'm going to take the derivative 2x minus 2 and then leave the original second function as it is. And then now switch the positions. Now you need to grab the first function, leave it as it is, and don't forget to have parentheses because this has multiple terms, and then take the derivative of this component, the second function. When you try to differentiate the second function, you can clearly see it is a function of a function. But when it comes to the interior function, you can see it has the product rule used in that component. So first of all, the derivative of the outer function is none other than cosine. The original function is sine. The derivative is going to be cosine. And then you have x squared ex. And then it's multiplied by the derivative of the inner function, the inner layer. That component is none other than just the product rule again. So that will give us 2x ex plus x squared ex. I do not intend to explain this computation separately because we already know exactly how each component would work in terms of uh, the examples that we have already seen in these different components. But what we have seen here, what we are seeing right here at this example is to putting all of these pieces together, all of those pieces together to compute the derivative of a slightly complicated function. So let's consider the next example. Now, I recommend for each and every of these problems, you spend a couple of minutes before looking at the solution, pause the video, you work with the problem yourself, and then come back and watch and see where you need any improvements. All right, in this case, this is the quotient rule right away, but for each component, I may need slightly uh, sophisticated differentiation components. So first of all, when I take the derivative of the top, the derivative of the outer layer, which is tangent, turns out to be secant square of ln of x times now the derivative of the inner function, which is going to be 1 over x, times the original bottom function, e to the x squared plus 2, and then minus. Now you're going to leave the top function as it is, tan of ln of x times. Now the derivative of the bottom function, we know the derivative of the exponential is exponential itself. So it leaves this, and then you take the derivative of the inner function of that component. So it's going to be just 2x. And when you do entire process, don't forget the denominator of the quotient rule, which is none other than the complete square of the denominator of the original function. Let's proceed to example number 3. Now, this is again a similar example. Here we have a composition with a few repeated applications. And when you get to this point, you can see it is an application of the quotient rule. So let's proceed. The outermost layer is ln. So the derivative of ln is 1 over x. But what you see inside ln function is exactly this entire component. So it is 1 over x, but that x is supposed to be what you see inside ln function. So I will write the whole component sine of x plus x over x plus 1. And then once you're done with that, now we are completely done with this outermost layer. Let's look at the next step. Sine. What is the derivative of sine? That is cosine. And then write down exactly the inside function as it is without changing. Now in the next step, you're trying to get the derivative of the inner function, innermost function, in other words. So when you compute the derivative of the innermost function, all you need to do is to use the quotient rule. So take the derivative of the top, that is going to be just 1 times the original bottom function, x plus 1, minus switch x times the derivative of the bottom function is going to be again 1. The whole thing is divided by complete square of x square plus 1. And you can clearly see there is a nice simplification that you can do in the numerator. X will get cancelled with x if you simplify. But even if you leave the answer in this form would be sufficient. And just make sure that you have, if you simplify it, there's a possibility that computer algebras would accept the answers better. But technically, your answer is correct once you get to this point. Example number 4. Another example for a combination. Now here in this case, you have, again, a quotient. The overview of the function is a quotient. But when you take the derivative of the numerator, you do have, again, a product. And then for each individual component, e to the 3x or sine 7x, you may need to employ the chain rule for individual derivative computations. So let's proceed. First of all, the recipe of the quotient rule is to differentiate the top. So begin with that. I will start with parentheses and take the derivative of, first of all, this entire component. Forget about everything else. Now we're trying to write down the derivative of that n-cycle component. So what would that be? 2x times e to the 3x plus x squared. Then the derivative of the e to the 3x is e to the 3x times 3 because of the chain rule. So that is the derivative of the top function multiplied by the original bottom function. And then minus, now the original top function times the derivative of the bottom function, where you're going to have the derivative of sine, which is going to be cosine of 7x times the derivative of the inner function 7. The whole thing is divided by the square of sine 7x, which is the denominator of the original function. So this is a combination of problems just to recall the interesting derivative computations. Let's proceed to an example where you can actually accompany the idea of the derivative, the meaning of the derivative. In particular, this problem is called the tangent line problem. The general overview of this problem is generally recognized as the tangent line problem. So the idea is basically to understand the use of the derivative in practical context. So find the equation of the tangent line to the graph given by this at this given point. The first thing that I'm going to do is now look at this. At this point, this simply means this is an x coordinate, this is a y coordinate. First of all, let's see whether this is meaningful. Is this point lying on this graph? I'm just curious. I'm just trying to check. If you plug the value of x here, x equals 2, right? If you plug x equals 2 in this position, in the position of x, what do you get as a computation? You will end up getting 2 times 2 here. It's going to be 8 in the first component minus 10 and then plus 1. So it will turn out to be just -1 when you simplify. So that is the corresponding y coordinate given. So that's why this is a meaningful problem to begin with. So this is what we are trying to do now. Look at this simple illustration. If you consider the graph of this function, I'm not too worried about the way it looks. Let's pretend that it looks like this. And at point 2, it says like at 2, it's -1. So 2 corresponds to a negative value, -1. So 2, -1 is on this graph. Now what you need to understand is the fact the tangent line, the slope of the tangent line, the slope equals, usually it's denoted by m. It is none other than the derivative. So it's given by the derivative, given by the derivative. And when you have the derivative and when you have the slope, don't forget you already have one point on the graph on the straight line, and now you have the slope. You can use the point slope formula to write down the answer. So let's do this process. The answer. First of all, now this is what I'm going to do. I'm not going to worry about any of these graphical illustrations. All I need to do is to compute y prime, the derivative, that is going to be 4x minus 5. But don't forget, I need y prime when x equals 2. That is exactly the value that I need to consider here for this point. And that is going to be my value of slope. So this special notation that I use here, after y prime, I put this vertical line segment and I put x equals 2. This is a shorthand notation to indicate that I'm about to evaluate y prime when x equals 2. So let's do that computation. I already know y prime is 4x. So 4 times in the position of x, I'm going to place the value that I'm considering, 2 minus 5, compute. 8 minus 5, it's 3. So now we have the slope and we know one point on the graph. So the point slope formula is y minus y1 equals m times x minus x1. In other words, x1, y1 are playing the role of this point, the coordinates of the point, and m is given by exact computation that we have seen already. So y minus the corresponding y coordinate is -1. So -1 equals, here m is 3 and x minus 2. You can leave the answer just like this, or you can simplify the answer to the form y plus 1 equals 3x minus 6. And if you simplify, now if you have this kind of a problem at a certain point, be careful. First of all, check the way that the answer is asked. Sometimes if the problem is just already having some field like y equals and you need to fill in this blank, then you need to write down exactly what y equals, right? So you can say y equals 3x minus 6 minus 1, it's minus 7. So you need to input 3x minus 7. Or if it is just giving you a complete blank and saying like, what's the answer? Then feel free to write it or input it in that form. All right, so let's proceed to another interesting aspect. Now, let me show you something that will connect with the upcoming module or the next levels of derivative computations. Now here, if you recall, uh, when we worked with trigonometric functions, when we had like some functions, if we simplified them before differentiation, we saw there is a significant simplification in our computations. Now, this is exactly the scenario with some of the functions whenever there are valuable simplifications are permitted. So this is exactly the situation where I'm going to employ interesting aspects of natural log function in our simplifications. So first of all, so let's recall this. If you do not recall it, I will exactly point out what you need to recall, which points you need. First of all, the function ln of x, it is defined none other than the log to the base of e, where e is exactly the same as the base of natural exponential function. So now when you consider this definition, it is an obvious uh, conclusion. You will come up with ln e, right? So whenever you compute the base, so log e to the log e to the base of e is none other than just 1. Whenever you compute the base of a log of the base itself, it will result just 1. So that is why you're seeing the second property. So the first one is the definition, the second one an immediate property, and then the simplification properties are exactly these three. So now let's pay attention. Let's have them, let's note it down on your notes, because in the upcoming conversation, we will use these properties in some computations and you will see how useful they could be. First of all, when you have ln and if you have a product sitting inside, if you have a multiplication inside, you can simply transform it to a summation. The price that you need to pay would be taking ln's of both of them. And then if you have a quotient inside ln, you can convert that to a subtraction. You can see the priority goes with the first term. So ln A and then minus ln B, which is exactly the term sitting in the denominator. So it is differentiated, or it is identified by the negative sign. And then whenever you have a power sitting inside an ln term, you can bring that power to the front. Now, since we have seen bringing the power to the front in a different context, where we had the power rule in differentiation, so please do not mix it up. This is just algebraic property. There is no reduction of power or anything. This is just purely and algebraically bringing a power to the front by employing properties of natural log. So now, assume these three properties. Assume. If you recall them, that's perfect. If you do not recall them, now let's assume it. Based on this, now look at this. Using logarithmic properties, find, using logarithmic properties for derivative computations. Now, compute the derivative of this given function. Now, look at this. What is the speciality of this given function? This function has an ln right in front. And if you try to do the computation right away, you can think about it, because this is a composition. Can you see this is the outer function? It contains this entire component. So it's not going to be a big deal. You can take the derivative just by known methods. But the problem is, if you try to do that, when you get to the level of the derivative computation of the inner function, it becomes significantly complicated because there are many moving components, many parts involved. Therefore, this is what I am going to suggest. Other than taking the derivative right away, why don't we use the properties of ln to simplify this? Step number one, I will just keep this operation of the derivative, like let's say d by dx. I will leave it. And then let's take the derivative of ln. Before taking the derivative, hold on. Right, before taking the derivative, let's simplify this component. Look at it. When you have ln a divided by b, now look at this. These two circles are exactly performing as a and b. So when you have a divided by b, you can see it is going to be ln a minus ln b. Let's pretend like these two are like uppercase A and uppercase B because these terms look big, right? It's going to be just like that. And then when you look at this component carefully, you can see it is a product. It's a multiplication, so you can further break it into pieces. And then when you get to this component, you can see it has a power, so you can bring it to the front. And then the same thing goes with this component. And then this component is none other than just ln of this. But don't forget, square root itself has a power representation. It is a power of 1/2. So now by employing all of these properties, let me show you exactly how we can simplify, what kind of simplification that we can have here. First of all, ln of x squared plus 3 raised to the 4, and then plus ln of 3x plus 7 raised to the 10. Now this is exactly after the decomposition of the top term over the multiplication, and then minus, you have ln of x squared plus 1 to the power 1/2. Let's buy a little more space here so that we can squeeze this right away to that. This is how it looks. And then there is this big parentheses. Let me use a different color. This parentheses should stay right there. Now, at this point, you can bring these powers to the front. The derivative of 4 times ln of x squared plus 3 plus 10 times ln of 3x plus 7, and then minus this 1/2 is also power, so I will bring it to the front, 1/2 ln of x squared plus 1, and with that we will cross the pink parentheses. Now look at this. At this point, you have only summations inside ln terms. That means you cannot simplify it any further. You can simplify when you have a multiplication or a division inside ln, but you cannot do anything when you have just a summation or subtraction. There is no such formula in the properties that we have seen. So what we are now trying to do is to distribute the derivative operation. Don't forget, you have summation and subtractions. So other than playing with the very complicated quotient rule in the inner function, now we can do the direct computation. Look at this. The derivative is going to be 4 times the derivative of this component. It is a chain rule. So 1 over x squared plus 3 times 2x. 2x is none other than the derivative of the inner function, plus 10 is the constant multiple. Take the derivative of the second component. That will result 3x plus 7. times 1 over 3x plus 7, because the derivative of ln is 1 over x, and then the derivative of the inner function is 3. And minus 1/2 remains as the constant multiple, and take the derivative of ln of x squared plus 1. So ln of x will result x squared plus 1 in the denominator when you take the derivative, and then take the derivative of the innermost function in that case, which is going to be just 2x again. Now you can have minor simplifications. What are the possible simplifications? Here 2 will get cancelled with the factor 2 there. And then combine these two constants, because that's a multiplication. Combine these two pieces and you can just write it in the final form. 8x divided by x squared plus 3 plus 30 divided by 3x plus 7 minus x divided by x squared plus 1. That is your final answer. Now, if you do not trust me about the significance or the convenience of this particular approach compared to direct differentiation of this function by using direct chain rule followed by the quotient rule, I invite you to give it a try and see whether or compare which method is going to assist you seeing what's happening and to get to the answer conveniently. So with that open end, I will move to the next conversation. Now, other wonderful implications. Now, these are not really just implications. In other words, look at this. What you see right here is the power rule. Now, we had the power rule, but how did we know the power rule would work? How do we know about the construction? How does this work? Now, let me show you a couple of illustrations here based on exactly what we have seen. In fact, the power rule has a wider scope where n need not to be just an integer, or it need not to be positive integer in particular. It could be any real, any positive real power that you consider. However, in this occasion, I will just, it could be any positive value, it could be any negative value, it doesn't really matter. It is just, it can be any real number. Now, to show you how it works only at least for positive integers, let me show you. First, don't forget the derivative of x is just 1. We know the graph of y equals x. The slope is supposed to be 1. And at the same time, by using the derivative definition, this is not something complicated to develop. And then if I compute the derivative of x squared, now look at this. Don't forget the derivative of x squared is none other than x times x, right? X squared is x times x. Now you can use the product rule. If you wish, you can use the product rule over this product. If you use the product rule, you're going to end up getting 1 times the derivative of the second function, which is going to be just x, plus now switch x times 1. So this is none other than just one copy of x, another copy of x, it's just 2x, which validates the power rule. Now, how can you have this line number 1 and line number 2, right? So we know this is correct, and we now know this is correct because we developed it. Let me ask you how it's going to be when you consider x to the 3. In that scenario, you can just break it into two pieces, x times x squared, and you know the derivative of x, the first function, it is just already 1 times now x squared, original second, plus original first and the derivative of the second, which is none other than now derivative of x squared. Don't forget we justified in the previous line. Therefore, I can now use it. I'm granted to use it. Even if I develop this function, even if I'm not granted to use this power rule now, of course, that is exactly what we're trying to develop here, right? So just simplify. Here you end up getting x square in the first case, and then this one is just 2x square. Altogether, it's going to be 3x square. That validates this for the next step. Now, if you'd like to proceed, you can keep up with this process. The derivative of x to the 4, you can simply say the derivative of x to the 4 is given by x square times x square. You know the derivative of x square for each case from step number 2, right here. And therefore, you can construct it, try it and see, do the work, and see if the product rule will result exactly 4x cubed. This particular process is called mathematical induction. This is not an induction proof. There are different ways or different methods in mathematics to establish mathematical statements. One particular method is called induction, mathematical induction, and that is just like climbing an infinite stairway. So this is exactly, now this has, you can consider in this occasion, there are infinitely many values that you can consider for n, but you can always get to the next step by considering the previous step, one step at a time. All right. So in that way, you do have an illustration. You can see why the power rule works. And then the next component. Don't forget, we had these formulas, right? The derivative of sine, cosine, and then starting from that, okay, so we had the derivative of tangent and we had a bunch of derivatives given in our formula sheet. But now, how are they constructed? Now, first of all, to begin with, we need to prepare the formulas for sine x, the derivative of sine x, which happens to be cosine x, and then the derivative of cosine x is none other than negative sine x. Now, I'm going to assume these two in this particular lesson. And these have mathematical proofs starting from limit definition. But now the purpose of this particular problem is not to establish these two formulas, instead to use them to establish the derivative of tangent. Now let me show you how it would work when you know the derivative of sine and the derivative of cosine. So the derivative of tangent is none other than the derivative of sine x divided by cosine x. Now, don't forget, you know the derivative of sine and you know the derivative of cosine. You do know the quotient rule. Now, let's use that. The derivative of sine, which is going to be cosine x, and then the derivative of, then you're going to combine it with the original bottom function, and then minus the derivative of original first function times the derivative of the bottom function, which is going to be negative sine x. The entire term is lying on cosine square, which is the square, algebraic square of the denominator. And with that, now let's simplify one more step. This is cosine square right here at the top. And then minus, together with this minus sign, would make it plus. And what you have with sine and sine is sine squared. The whole term is divided by cosine squared x. And what is sine square plus cosine square? In other words, cosine square plus sine square, cosine squared x, it should be. So what is the cosine square plus sine square? That is the Pythagorean identity, which is none other than just 1 divided by cosine square, and that will result Exactly. 1 over cosine is secant, and this has a square, so it's secant squared. And that's how you can develop a formula starting from what you know to get to the unknown. So let's pretend that we prepared the derivative of sine and derivative of cosine, and then how can we get to the derivative of tangent? It is nothing other than the quotient rule. And then one more attempt. What is the derivative of secant? Let's prepare this. The derivative of secant, first of all, we know the derivative of sine and cosine. Let's pretend that's all we know. And then 1 over cosine x. Secant x by definition is 1 over cosine x. Now let's take the derivative. You can employ two different methods here. You can either use the uh, chain rule by considering cosine to the negative 1 power, or you can use just the quotient rule. Look at this, use the quotient rule. If you use the quotient rule with one of the functions being a constant, now when you take the derivative of 1, that would be just 0 multiplied by the original bottom function minus, then you have original top function multiplied by the derivative of the bottom function minus cosine x. The entire term is relying on the square of the denominator, which is just an algebraic term. And then now look at this. The first component has 0 multiplication, so that will just disappear. And then minus times minus would make it plus, and you're going to get cosine x. Oh, here I made a mistake. Let me correct it right away. Here I said the derivative of cosine, that's exactly what I wanted to write here. I said it's derivative of cosine. I wrote it like negative cosine x. It is supposed to be negative sine x. Since it's a correction, let me do it in red color. Let's employ red, and then let's erase this cosine. And it is supposed to be negative sine x, the derivative of cosine, right? So that should be what you're going to see here, sine x at the top, divided by the square of the denominator, which is cosine square. Now here you have two copies of cosine in the denominator, one copy of sine in the numerator. So let me separate them in this form. 1 over cosine x times sine x over cosine x, which is going to be the same, right? If you multiply the denominator pieces, that would result to a squaring. And if you multiply the top, it's going to be just sine x, which is just the same thing. However, now when you write it in this form, you can clearly see this is none other than secant x, and this is none other than just tangent x. So the purpose of these last couple of illustrations to make meaning for these formulas is not exactly to question the formula collection that you already have. It is just to reduce the amount of material. Now, if you're really would like to have, if you really prefer having logical thinking rather than just any kind of memorization, mathematics is an excellent playfield. Calculus is an amazing playfield. Look at this. Here you can start with a few different derivatives to begin with. Like, let's say, to analyze all trigonometric items, you can start with the derivative of sine and derivative of cosine. That's all you need. Starting from that, if you know those two components, you can start from there. You can construct any other derivative formula that you need. Let's pretend that you forget one of the derivative formulas at a certain point, but you know the basics, the sine and the cosine, your two best friends in trigonometric world. You can employ them to analyze or to develop any other component. So that is the beauty behind the sequential, or like being in this derivative compartment. You can pretty much like see these interconnections, and you can further summarize it to see the beauty and the simplicity of these concepts. However, the price that you need to pay would be simple knowledge from those knowledge bases. For instance, when it comes to uh, previous computation, you should know the Pythagorean identity. Cosine square plus sine square equals 1. Similar to that, here in this case, you should recall secant is none other than 1 over cosine x. As far as you recall those basics, you can just develop these formulas from scratch. So that's exactly where we're going to conclude this conversation. And as a summary, we began this lesson with a couple of mixed derivative computations. And then we worked with one example where the geometric notions of the derivative, in other words, the tangent line problem, is employed. And then we considered a few examples um, of like developing formulas that you saw right now. And beyond that, we worked with one example where you can employ amazing properties of natural log to come up with an easier derivative computation when you have higher powers and multiplications and divisions. So please review them and work with a few examples in that way. Like there are examples, there were examples given in practice problems. Work with them and have good practice. And I will see you in next lesson.